Hey everybody, hope you are all doing great. So our next lesson in this series is now on applications of sinusoidal functions. This is very similar to what we did yesterday. What we did yesterday was we were building equations, and in order to do that, we had to figure out the A value, the B value, the C value, and the D value. A, B, and D always stayed the same, but then the C value would change depending on what type of an equation that we wanted to draw. Remember that a sine graph had to start on the midline and head up. A cosine graph had to start on the max and head down. A negative or reflective sign had to start on the midline and go down. And a negative or reflective cos had to start on the minimum and head up. So what we're going to do today is we're going to take that knowledge of building equations that we learned yesterday, and we're going to apply it to real world applications. Your diploma loves asking sinusoidal application questions. Sometimes you'll see a question that involves a Ferris wheel, like we're going to start with, but really it could be any sort of spinning circle. So I've seen Ferris wheels, I've seen water wheels on boats, I've seen wind turbines going round and round, I've seen ceiling fans going round and round. Anything that spins can create an application question, okay? So I want you to open up your books to this section, and we're gonna start in with the first question. It says a Ferris wheel has a radius of 5 meters, and its lowest point is 0.5 meters above the ground. Sam gets on at the bottom of the Ferris wheel, and it takes 8 seconds for Sam to travel from the bottom to the top. So let's just, before we go any further than that, let's just draw a picture of what we're talking about. So here's the ground, and here's the bottom of the Ferris wheel. Okay, so we know that the bottom of the Ferris wheel is 0.5 meters from the ground. Can't have a Ferris wheel on the ground or it would scratch the ground up or scratch the Ferris wheel. Now, it says it takes Sam 8 seconds to go from the bottom to the top. Now, what I want you to visualize right away is that's not a full rotation of the Ferris wheel. That's actually half a rotation. In a couple minutes, we're going to talk about a period. The period is not 8 seconds. The period is going to be how long it takes to go back to where I started, right? So the period is actually going to be 16 seconds. We might as well write that down since we're talking about it right now. So period is 16 seconds. Now, that means if it took 8 seconds to get up here, it's going to take me how many seconds to get halfway up there? Well, to get halfway up there, that'll be 4 seconds. And we want to kind of think about, well, how high am I at those 4 seconds? Well, I know I have to be for sure that 0.5 high. But then I've also added this distance. So we need to kind of visualize, what does that distance mean? Well, that distance puts me right at the center of the Ferris wheel. Do you have a word in your head for going from the center back to the outer edge of the circle? That's the radius. So we know that this piece here has to be 5. So we know that at 4 seconds, Sam is now going to be 5.5 meters high because I have the 5 of the radius and I have the 0.5 that I was off the ground. Okay, so I'm going to pause that there. I'm going to just go back to the question for a second, but we're going to use that in a sec to start filling in our table. So we're going to examine the relationship between Sam's height above the ground and the time that he's on the Ferris wheel. Complete the following table of values and sketch the graph to the right. Now, before I switch the slide, just a note here, your calculator does have to be in radian mode. So there's never real world applications that you do in degree mode. You always want to be in radian mode. So just as a check, make sure on a TI calculator you press mode, go down 3, and it should be the word radian highlighted. On a Casio, you're going to press shift and then menu, go down to angle, and make sure you select radians. Okay, so here's our table, and we started you off with that 0.48. Well, now you know why we started you off with that 0.48, because at 0, I'm beginning, and then at 4, I'm at the quarter mark. At 8, I'm at the top mark, or the halfway of my period right now. Then the next one we're going to look at would be 12, and we're going to just keep going up in increments of 4. Okay, as far as the height, we start at 0.5. At that 4 seconds, we're at 5.5. At that 8 seconds, we're at the very top, which means we have to add another radius. So adding another radius puts me at 8 seconds and 10.5 for the height. Then I'm going to start going back down. So at the 12-second mark, I'll now be back to 5.5. And at the 16-second mark, I've completed 1 revolution, which means I'm back at the lowest point, which is 0.5. So I want you to pause me for a sec, fill in that table. Awesome. So this is the table that you should now have filled in. You can just take a look and make sure your numbers match my numbers. And we're going to take that and graph it on the graph that's to the right of your page there. So all we have to do is plot those points. So here I've gone and I plot each one of those points, and we immediately see this sinusoidal wave. Okay, so we're going to connect those dots with a sinusoidal wave. Make sure when you do that, that you have a nice curve to it, right? You don't ever want the line connecting here to here to be straight. You don't ever want the top or the bottom to be pointy. You want a nice curve feature like this. If you can see my mouse going along there. Okay, so once you've drawn that in, it should look something like this. I also stuck my midline in there because in a minute we're going to build the equation anyway, so it's good to have the knowledge of what that midline is. Okay, so let's take everything we just said and put it into an equation. The equation we're asked to draw is a sine equation. So I need to think about, okay, what's A, what's B, what's C, and what's D? Well, A we know for sure. That ended up being, if you think about this as your midline here, that 5.5, from there I go up 5 to the top and I go down 5 to the bottom. So A ends up being 5. The other thing that we just realized there, or I don't know if you've realized it or not, but you do right now, the radius of the circle in these real world applications really becomes the amplitude, okay? So A is gonna be 5. Now, B, we already talked about the period. The period is 16 seconds. Reminder from yesterday, B is 2 pi divided by what your period is. So we're gonna have 2 pi over 16, and then that would reduce to pi over 8. Now, for C, I'm looking at a phase shift. I want to do a sine graph. So if you take a look at my mouse, a reminder that sine starts on the midline and heads up. So this is my starting value for sine, which tells me this guy here is my phase shift. So I have a phase shift of 4 if I want to draw a sine graph. And then lastly, D we've already talked about. D ends up being the distance from the center, sometimes that's called the hub, the center of the Ferris wheel down to the bottom, which is going to give me that 5.5. So when I put it all into an equation, my equation ends up being h of t equals 5 sine of pi over 8 times t minus 4 plus 5.5. If you'd like to have that in another set of brackets there too, so you can see the double factors or the double brackets there, that's great too. Okay, now describe how the parameters of A, B, C, and D relate to the Ferris wheel. Well, that's kind of what we just talked about. We're just going to put it in writing now. A is your radius. B, you got to be careful with B. Don't tell me that it is the period. B is never the period, right? But it's related to the period through that formula. 2 pi over B is your period, or your period is 2 pi over B. So we're going to say that B is related to the length of time it takes the Ferris wheel to complete 1 revolution. Remember that B is 2 pi over P, or P is 2 pi over B. Okay? Now, for the sine graph, we had a phase shift of 4 seconds. Now, in the context of this Ferris wheel, that is the time it takes to reach mid-height, because I started at the bottom height. Okay? The other thing I kind of want you to see about that right away is if we're starting at the bottom, the sine graph starts a quarter of the way away. And that's good to know, because sometimes then you don't even have to draw it. If you know your period is 16, you can just say, hey, okay, a quarter of 16 is 4. My sine graph will start at 4. All the important points in a graph, your minimum, your midline, and your maximums, they all create these little pieces on the graph that are a quarter of a period. So from your midline to your max is a quarter of a period, from your max to your midline, quarter of a period, midline to min, quarter of a period, and then min to midline, quarter of a period, okay? And then D is the height of the center of the wheel above the ground. And again, sometimes that's called, you might want to make a note that sometimes that's called the hub, okay? Okay, the next question says use your graphing calculator to determine the height of a rider at 9.3 seconds. So you're always asking yourself, okay, were you just given an X value or a Y value essentially? Now in the context of this question, that's a T value or an H of T, but it's the same sort of setup. You are given a time value here, so you can just plug that right into your equation. I've taken the equation, I've replaced T with 9.3, and now I'm just gonna solve it. So you can plug all that into your calculator, and you'll get H of 9.3 is 9.9 meters. So at 9.3 seconds, Sam will be 9.9 meters off of the ground. Okay, and the next question says, use your graphing calculator to determine how long the rider is 9 meters or higher in one full revolution. Now, this one takes a little bit of visualization, and just give me 1 second here because I want to put on a pen so I can draw for you. So if you think about this, here is the 9-meter mark, okay? And you're being asked, how long am I gonna be above 9 meters? Well, at this point here, I begin to be above 9 meters, and at this point here, I stop being above 9 meters. So what you have to do is you have to find those timestamps. You have to find the X value of both of those spots, and then just subtract them. If you subtract them, that's the total time that he's above 9 meters. So I'm gonna do this via graphing calculator. If you have a TI, you can put 9 into Y2 and then solve for those 2 intersection points. You can also do that with a Casio, but a Casio also has a built-in Xcalc feature, so if you wanna do that instead, that might be a little quicker. Sorry, I'm just, I'm new at these toys and I'm trying to figure out how to turn off my, oh, there's my mouse. Okay, cool. So those were the instructions for the calculator. And then the numbers that you should have gotten are 10.03, that would be this guy over here, where I stop being above, and then minus 5.97. The 5.97 represents where I started being above. And so I get a total of I'm above 9 meters for 4.1 seconds. Okay. All right. Then it says express it as a coast graph instead of a sine graph. Well, look at what I've done here. I've kept A, B, and D there because remember, those guys don't change. If I'm now looking at it as a coast graph, well, a positive cos starts at the top and then heads all the way down. So right there, I have a phase shift of 8. So my C value would be 8, and my equation would look like this. But now, and some of you may have already caught this, there's an easier cos graph to draw or to create. There's an easier cos equation to establish. And that would be actually the negative cos, because the negative cos starts on the minimum and heads up, which means there would be no phase shift. Okay, so I just noticed a quick little error here. Just make sure that says negative there, okay? I can draw that in for you if you like. So there should just be a, oh, no, I can't draw it in. Sorry. Okay. It's all good. Okay, so the following graph represents the height above the ground of one of the cars on a Ferris wheel. Determine the height of the hub or center of the Ferris wheel. Now, the height of the hub, that sounds like the D value to me. Well, if I'm looking at a D value, I'm taking the average of the minimum and the maximum. So I just add the min and the max together and divide by 2. So that gives me 10 meters. Okay, then we say determine the radius of the Ferris wheel. Well, we talked about the context of all these guys. The radius actually is your A value. So to get your A value, you would take your the maximum minus the minimum, so you get the full distance there, and then divide that by 2. Or if you want to just draw in your d value and count how far up you have to go, that's perfectly fine as well. Okay, just make sure you're communicating what you're doing. Okay, then state the period of the Ferris wheel. Well, I can actually see that right off the graph. The period's 100 seconds because I start at this minimum here and then I go to this minimum here. So total period would be 100 seconds. And now it asks me to create an equation. So I know the A was the radius, and I've already established that, that's 5. B, well, I know my period is 100 seconds, so that'd be 2 pi over 100, which would be pi over 50. The D value we also established was 10. Now, to do a C value, if we're looking at sine, remember we said that if we're starting at the minimum here, the phase shift for sine is actually going to be 1/4 of a period. So if my period's 100 seconds, the phase shift's going to be 25. And then for cosine, if I'm using a positive cosine, it'd be half the period. So my phase shift would be 50. So then those two equations would look like this. And then again, is there a simpler version? Yeah, we could do the reflective cosine, which is -9 cos of pi over 50 t plus 10. All right, so the next one that I have in here, I just kind of want to talk to you with. This is not in your book, so don't look for it. But I wanted to give you a question where there's a bunch of letters and just see how you handle the letters. So it says a Ferris wheel has a radius of r meters. The center of the wheel is z meters above the ground, and it takes w seconds to complete 1 full revolution. If the rider starts at the bottom of the Ferris wheel, write an equation in those forms for the height in meters of a Ferris wheel car as a function of time. So again, we're just thinking, what's our A, what's our period, what's our C, and what's our D value? Well, if I have a radius of r, I know that that's A. We are told that the center of the wheel is z meters above the ground, so that's actually my D value. And we're told it takes w seconds to complete 1 full revolution, so w is the period, so I can replace the p with w. So when I do that, the equations look like this. Here is the sine one. Remember I said that the phase shift for sine would be 1/4 of a period away. Well, I don't know what the period is, but I know it's w, so 1/4 of that would be w over 4. And then for cos, you can look back at the graph you just did with numbers to reference, but the phase shift was always a half a period for cos. It took us half a period to go from that minimum up to the maximum. And so if the period's w, half of that would be w over 2. Okay, and then kind of a second part to this question, I'll leave the equations there for you, but it says determine an expression for the height above the ground of the bottom of the Ferris wheel. So really, that's my minimum point. How do I get to my minimum point? Well, in any trig graph, if I want to get to my minimum point, I could start at the midline and then just head down the amplitude. That would always take me down to my minimum point. So the midline would be D in a regular equation, and the amplitude would be A. So I would find my minimum by going D minus A. So now in the context of this question, my new D is actually Z, and my new A is actually R. So I would say that I would find the minimum point by going Z minus R. Okay? Awesome. Now, next question, I'm back into your book. At a small ocean port, the water has a maximum depth of 18 meters at 7 p.m. and a minimum depth of 8 meters 6 hours later. This scenario models a sinusoidal function where t is the time in hours after 7 p.m. and h of t represents the depth of the water. So the first thing we want to do is graph this scenario. Now, we didn't give you a grid for this because we wanted you to kind of think through what you're going to have to do. We're talking about a day. We're talking about going from a max to a min in 6 hours. Well, first thing I want you to think about is a max to a min is not a full period. That's only half a period. So a full period is going to be 12 hours. But since we're talking about a day, we might as well go 24 hours and just look at the whole day, okay? Then as far as your your X scale then should go from 0 to 24 is what I'm saying. As far as your Y scale, I need to hit a maximum of 18 and a minimum of 8. So as long as I'm going from like 0 to 20 or something like that, that should be good. So now this is kind of the window I'm going to work with as I draw this stuff. I'm going to ask you to pause me. I want you to generate some points, try and draw the graph, and then take a look at mine. And mine ends up looking like that. Okay, so now the next thing we're going to do is we're going to try and figure out the cosine equation. So again, we want to figure out, okay, what's A, what's B, what's C, what's D? Well, A, we know that we go from a depth of 18 to 8. So in total there, that's a span of 10. So A is going to be 5. Your B value, well, we just said that the period takes 12 hours. So your B value would be 2 pi over 12, which would be pi over 6. I'll skip C for 1 second, go right to D. The D value has to be the halfway point between 8 and 18, which is 13. Now you could do that by taking the average of 8 and 18. 8 plus 18 is 26 divided by 2. Or you could say you already know your A value of 5, so I could go to my minimum, add that 5, and get up to 13 that way. Now, we are asked to draw a cosine graph, and so cosine graphs start on the maximum, and this guy does start on the maximum for the y, on the y-axis as well. So that means there's no phase shift, so C is 0. So I've got all that, and then my equation becomes h of t equals 5 cos of pi over 6 times t plus 13. Now, we're gonna just talk about a couple of questions that go with this. The next one is determine the depth of the water to the nearest tenth of a meter at 5 p.m. So now the trick to this is you have to remember that we based this whole thing on the hours after 7 p.m. So 7 p.m. is time 0 right now. If 7 p.m. is time 0, I have to figure out what 5 p.m. is. There are 2 different ways I could do that. I'm hoping you're yelling an answer at me at the moment, but I could go -2 because it's 2 hours before 7 p.m. Or I could say 22 because it's 22 hours after 7 p.m. So both of those would work. Both of those would give you the exact same answer. Now that's a t value. So I could use my calculator or I could just plug it in and solve. Either way, you should end up with an answer of 15.5 meters for the height at 5 p.m. Okay, and then the last question here, this one's a much harder one. It says determine the first time after 9 a.m. that the depth of the water is 10 meters. Okay, well, we got to kind of talk through this for a second. If 7 p.m. is time 0, 7 a.m. is 12 hours later. 12 hours to go from 7 to 7. Okay, so 9 a.m. is 2 hours after that. So this is really saying determine the first time after x is 14, the 12 plus the 2, determine the first time after x is 14 that the depth of the water is 10. So if you take a look at my mouse, here's when x is 14. I'm looking for the first time after this point that the depth of the water is 10. So I'm essentially looking for this point right here. So you're going to use your graphing calculator for that. But just remember that if you don't put your cursor over there, if you're a TI, if you don't put your cursor over there, it's going to take you to the left one. So you have to make sure your cursor goes over to the one you want first. If you're a Casio, you have an easier job because you're going to solve it and it's going to go to the one on the left, but then you can just press your right button until you're at the one you want. Either way, the message I'm trying to say is don't take the first one you see, make sure it's actually the one you want. So go ahead and do that. And your answer should have been 16.23. So now, the last thing we have to have a little conversation with on this, hey, Mr. Wolf, what time is it? you have to take the t value of 16.23 and you have to transfer that to an actual time. So the 16 is decently straightforward. That means 16 hours after 7 a.m. Or sorry, 7 p.m. Because remember, 7 p.m. was time 0. So 12 hours after 7 p.m. is 7 a.m. I got another 4 to go. So I'm looking at 11 something. Okay, it's 11 something in the morning because that's 16 hours after 7 p.m. the night before. It's not 11:23. What you have to remember there is that actually means it's 0.23 of an hour. An hour has 60 minutes. So I need to go 60 times 0.23. I have to essentially take 0.23 of 60 minutes and figure out how many minutes that is. That ends up being 14 minutes when rounded to the nearest minute. So it's 11:14 in the morning. Okay? All right. The last question, you might go squirrely on. Okay, the number of squirrels, n, living in a particular area can be modeled by the function n of t equals a cos of b t minus c plus d, where t is the time in months since the measurements begin. At 5 months, the squirrel population reached the first max at 200. So there's a point. You know you've got 5, 200. I'm just going to write that for our reference. I've got the point 5, 200. Okay. Then at 12 months, the squirrel population reached a minimum. So I know at 12, I'm going, what was it? 110. Okay. So this tells us lots of information, but the question is essentially asking us to find A, B, and D. So let's talk, we're just going to do it in that order. In order to solve for A, remember that we have to figure out the full distance that the y is traveling. So the distance from your minimum to your maximum. So if I'm going from 110 to 200, that covers a full distance of 90. A would have to be half of that. So I take half of 90 and I get A is 45. The B value, well, remember I'm going from a maximum to a minimum. That's half of a period. So from 5 to 12 is 7. So 7 months is half of a period. A full period would be 14 months. So the B value would be 2 pi over 14, which would then reduce to pi over 7. Lastly, the D value, well, the D value has to be the average of these two guys, average of your minimum and your maximum. So I add them together and divide by 2, and I get a D value of 155. Okay? Awesome. So your task for homework is to get through 205 to 213. And I hope this was helpful. You guys have a great day, and we will chat very, very soon. Bye.